we know about the stages and we are going to interconnect the stages. And that seems to be, let's say, quite logical. You just connect them one to another, but many errors are made in interconnection of stages. A proper cascade connection of stages is when the input of each stage is connected to the output of the previous one. And if you would draw a block around it, then you have a 4-terminal thing or a 3-terminal thing, but not 5, 6, or 7. And only a port, input port current and an output port current, and no current through the whole thing from the input to the output port. That is proper cascade connection. Then the whole thing can be described as a natural two-port, and that was our starting point for designing negative feedback amplifiers. Now, we cannot always achieve it, but then you are aware at least of what kind of errors we make. So let's put some 2 stages together that we have now and see if we can manage this, if we can do this. And I made a few that are, let's say, not as good as we would like to have, but then you also see what kind of errors you can make. So first of all, this one. This is a nice one. You never see it. And there's a good reason for it. You see, I have a 4-terminal element with 2 transistors. But the port isolation between the input and the output port is really bad. You can see that there is really a path from the control input from the second device. So the second device, could be VGS, connects directly between the output port and the input port. So the voltage across the between the 2 ports is now controlling also the output current. So this has a very bad port isolation. But if you would add a transformer here at one of the 2 ports, you could just use it. This is another one that is often used, but this is not proper cascade connection because I'm missing the return current. The current flows, but where does it go back? Probably through the feedback network. So this can never, let's say, this introduces errors that are not described by the negative feedback model that we have. This is a proper thing. Here we have an input and an output port, and the input current flows in the input port and the output current flows in the output port, and nothing flows out of the box. And of course here in the other one, just to flip the differential pair in place, you have the same. This is also a good connection. It doesn't mean you cannot apply the other ones, but you should be aware of what you're doing then. So that is how to connect and interconnect stages. And this, of course, is a completely balanced one. Then we have a few things maybe you never thought of. 4-terminal controller options. Let's look at maybe the second version here. There's or the third and the fourth. There's a strong asymmetry between the positive and the negative input, because you see there's here in the third one is the gate and the other one is a source, but you still have four terminals, an input port and an output port. So I could flip the whole thing around, not input and output, but plus and minus, and have the same solution. Which one do I connect to the source and which one to the feedback network or to the ground? So let me do some examples. Reverse connection of both the input and the output port. It means I do this. I just flip it around, you see? And I call the plus the other terminal. Or I do it with this one. And I call the other one a terminal. And I do it here. Now let's practice it for the first one, because that is really nice. You see here, I have this, I made a voltage amplifier with this controller. So a part of the return current flows through the network. You can read about it in the book, how you treat this. But you see in the source is connected to the base of to the gate, and the output is connected to the drain or collector if this is a bipolar transistor. But I can flip the whole controller around. I can do it like this. And the whole amplifier is still the same if everything is isolated, but it looks completely different. So that is a nice thing you should be aware of. Maybe it has consequences. It doesn't mean it behaves the same, because all bias circuitry here is omitted. And maybe the influence of bias on the noise and the distortion and parasitic capacitance is different at the different locations because you connect your bias sources to other impedance levels. So there can definitely be a difference between the two, but you can consider one or the other. And if you don't consider extra external components, no reason to distinguish one from another. So then we have some port isolation issues. Sometimes you connect stages and suddenly there's internally in your amplifier some wire going to the power supply. People like to connect gates of cascading transistors always to power supplies. Well, they don't belong there. Um, but that is what you're doing. You don't have your two-port anymore. You're pulling current out of the two-port. So that is another error. You make an internal ground connection and the two-port conditions are no longer valid. So what you assumed by designing your amplifier with loop gain is not, and the ideal gain may differ from the asymptotic gain and from the actual gain that you have. Maybe it's easier for biasing. Well, you still can do it as long as it's good enough, but you should be aware of what you are doing. That's the most important thing of doing those things. Another thing is if you have a balanced input stage and, for example, an unbalanced output stage, you just connect the output of the balanced stage to the input of the unbalanced stage. But your balanced stage has some common mode transfer. In that case, the common mode output signal is one terminal flows into ground and the other flows in your unbalanced stage. So it's converted into a differential mode signal. That makes that your common mode reaction ratio is limited by doing so. So it is basically, you are converting a common mode into a differential mode signal.